Section 8.3, graphing f of x equals ax squared plus bx plus c. The parabolas we've looked at so far have been of the form f of x equals ax squared or f of x equals ax squared plus c. The introduction of a into the equation created a change in the shape of the parabola, either opening up or down, or opening wide or narrow. The introduction of c allowed us to move the parabola up and down along the y-axis. By introducing bx as a middle term, a linear term, we're actually able to move the parabola around even more, so that its vertex could be anywhere on the coordinate grid. Now, based on the equation f of x equals ax squared plus bx plus c, there are two things we can find pretty much right away. The y-intercept is always going to be found by using the point 0, c. This makes sense because if you remember when we originally did the equations of lines, y equals mx plus b, we found that the constant added on to the end was the y-intercept. This is the same thing right here. If I replace x with 0, my first two terms will disappear, leaving me with just c. This is shown in the diagram where y equals 2x squared minus 12x plus 8 is our equation. The constant term 8 also serves as our y-intercept. The other thing that we can determine is the axis of symmetry. Now the axis of symmetry, remember, is a vertical line that passes through the vertex of this parabola. The equation that we're going to be able to use is x equals negative b over 2a. Negative b over 2a is going to be something that I'll figure out based on my equation. Since I'm told that y equals 2x squared minus 12x plus 8, I can use the equation x equals negative b over 2a to figure out the equation of the axis of symmetry. Negative is always going to go in there, and b is going to be the coefficient of the x term. In this case, it's negative 12. So even though that's a negative 12, I'm going to make sure that I put my negative in there that always goes with my equation. Then I'm going to do 2, and I'm going to say a is the coefficient of the x squared, which is 2. When I simplify this, I get 12 over 4, which equals 3. X equals 3 is the axis of symmetry. And that would just be the vertical line that would pass through the vertex. Now we've talked about how when we have the axis of symmetry, we can figure out almost anything else from the parabola. In this case, what we could do is we could realize that the axis of symmetry, being x equals 3, passes through the vertex and therefore corresponds to the x-coordinate of the vertex. Since we have x equals 3, we could plug that into our equation to determine what the coordinate would be for y at the vertex. In this particular case, I'm just going to plug in y equals 2 times 3 squared minus 12 times 3 plus 8. Now I just go ahead and I simplify this. Order of operations tells me I have to do 3 squared first before I multiply. And then I'll do 2 times 9 is 18, minus 12 times 3 is minus 36, plus 8. And when I combine these, 18 minus 36 is negative 18, plus 8 is negative 10. And so that negative 10 corresponds to the y-coordinate of my vertex. 3 came from my axis of symmetry, and that was the x-coordinate. Negative 10 came when I took that 3 and I plugged it back in to find what y was. So that's all you have to do. Alright, we're going to do what we have to do here to create a sketch of the quadratic function. Sketch doesn't need to be perfect, it just has to be a rough idea of what this looks like. We start with f of x equals 2x squared plus 8x minus 1. First I want to determine the axis of symmetry, and that comes from using the equation x equals negative b over 2a. In this particular case, my b is 8 and my a is 2. When I simplify that, I'm going to have negative 8 over 4, which reduces to just negative 2. That means that the axis of symmetry is x equals negative 2. Because that's the axis of symmetry, that's also the x-coordinate of the vertex. To figure out the y-coordinate, I'm going to plug that into my equation, basically finding f of negative 2, which is 2 times negative 2 squared plus 8 times negative 2 minus 1. When I square the negative 2, I get 4. Times 2 is 8. 8 times negative 2 is negative 16. And then I have the minus 1. 8 minus 16 is negative 8. Minus 1 is negative 9. So the vertex is going to be the point negative 2, negative 9. The y-intercept, remember, comes from the value of c. The y-intercept in this case is 0, always 0, negative 1. Now I want to look at my value of a to determine if the parabola should open up or down and wide or narrow. Since my a is 2, which is positive, it's going to open up. And because the absolute value of 2 is greater than 1, this is going to be a narrow parabola. Now I can take this information and provide a sketch. So let's see what we can do here. Zoom in and try to plot these points. I'll start by plotting my vertex, which is going to be at negative 2, negative 9. And then I'll plot my y-intercept, which is 0, negative 1. And I can see that this should actually follow through on what I had originally said. This is going to open up and be somewhat narrow. I'm just trying to draw a little sketch here and connect through that way, and then keeping in mind kind of the symmetry of this whole thing, we get a figure that looks something like that. Again, this is just a sketch. It's not a perfect graph, but it's a good representation of approximately what the parabola would look like. It opens up, it's narrow, it has the vertex of negative 2, negative 9, and a y-intercept of 0, negative 1. If we want to provide an actual graph of a quadratic function, we want to do better than a sketch. So, one thing that we can do is pick points for x. The problem is that if we don't pick points that are near the vertex, we might not know exactly how and when this parabola turns around. That can be problematic, but remember that we can always find the vertex first by using the equation x equals negative b over 2a. Pause the video, try to figure out the coordinates of the vertex, not just the x, but also the y, and then come back to check your work. All right, let's see how you did. The coordinates of the vertex are 1, 2. Didn't get that? Try again, making sure that you correctly deal with any negatives and that you follow the order of operations when plugging in x to figure out what y is. Now what we're going to do is we're going to use the vertex as the center point of a table. And we're going to figure out the other values that we want to use by moving away from the vertex. So I'll start by putting 1, the x-coordinate of my vertex, at the center of a table. Now, because I figured out the coordinates of my vertex, I happen to know that when x is 1, y is 2. So now what I want to do is I want to move away from the vertex to the right and to the left. Well, if I move to the right, I'm going to have 2 and 3. And I could add another one if I want. 2 more should be sufficient. And if I'm going to move in the other direction, I'd move backwards and I go to 0 and negative 1. So now I can pick how to plug these in. I'm going to start by plugging in 0 because that's such an easy one to plug in. When I plug in 0 into this equation, what I'm going to find is that the first 2 terms will disappear. It will leave me with 5. So I'm going to have a 5 right there. Now, because I know about the axis of symmetry, which passes directly through this value of x, I know that the parabola is symmetric on either side of it. So since 0 and 2 are just mirror images on the other side of 1, well, I'm going to end up having the same value for y at each of those points. So that's how I can fill in that that point will be a value of 5. Now for -1 and 3, I've got to choose which one I want to plug in. Doesn't make a difference which one. Maybe we'll choose -1 because the number is smaller. So for this, I'm looking at y equals 3 times -1 squared minus 6 times -1 plus 5. The -1 squared is 1 times 3 is 3. -6 times -1 is plus 6, and then I have a plus 5, and that's going to simplify to 14. So what I'm able to do is put in 14 in each of these spots, and you could check 3 to make sure that it would work out, but trust me, it does. Now we need to plot these points on a coordinate grid. So let's zoom in and take a look at this graph. We're going to plot these points one at a time. We'll start with 1, 2. And then we'll put on 2, 5. And 0, 5. Now we actually don't have enough room on here to plot 3, 14 and -1, 14, but we can see that they'd be somewhere over in this area. The 3, 14 would be up here, and -1, 14 would be up here. So it kind of fits our diagram here. And if we just connect through these points with a smooth curve, I just barely missed that one. You can think that that's probably good enough there. We have a narrow parabola that opens up, and it has its vertex at 1, 2. And that's how you graph the parabola given the equation. Find the vertex, move out from there, and just plug in points. All right, can we determine the characteristics of a quadratic function without the graph? Well, let's start with g of x equals -4x squared minus 24x minus 19. From that, are we going to be able to determine the domain, range, and a maximum or minimum value? Well, the first one is easy. For the domain, it's almost always going to be all real numbers, and it's no different here. So we can use that symbol to represent all real numbers. For the range, though, that often has a restriction, and with a parabola, that restriction is based on where the vertex is. So what I'd want to do is I'd want to figure out the vertex of this parabola. To do that, I'll start off with, once again, using my same formula, x equals -b over 2a. The b here is -24, so I've got -24, all over 2a, which is 2 times -4. And this is going to simplify to be a positive 24 over -8, which reduces to -3. That's going to be my x-coordinate of my vertex. And so to figure out the y-coordinate, I need to figure out what is g of -3. G of -3, I just plug into my equation, -4 times -3 squared minus 24 times -3 minus 19. So now I just have to simplify. First I square the -3, which is 9. Multiplied by -4 is -36. -24 times -3 is a positive 72 minus 19. And then -36 plus 72 is 36. And then 36 minus 19 is 17. And so the coordinates of my vertex are -3, 17. Well, that's going to affect how my range is determined. Because I look at the equation and I notice that the lead coefficient here is -4, that tells me that this parabola is going to open down. When something opens down, it's going to have a highest possible value. That highest possible value is going to be what the vertex is. The y can be anything below that maximum value because we're going to continue on infinitely. That means that my y here can be anything less than or equal to 17. That's my range. Connected to that is the idea that this is going to be a maximum. Anything that opens down has a maximum, not a minimum. If it was a parabola that opened up because the lead coefficient was positive, we would have a minimum value, again, located at the vertex. In this case, I have a maximum value, and when I'm talking about maximum, I'm talking about the y, so my maximum here is 17, which is connected to both my range and my vertex. We can take a look at a graph of this function to confirm our findings. You can see here that the domain is all real numbers. The range is y is less than or equal to 17, and the maximum is 17. Here's my vertex at negative 317. I'm going to continue down infinitely, both to the left and to the right, meaning that my range can be anything below 17 or including 17. And since I can always go to the left and the right, that's why my domain is all real numbers. I hope this makes sense. All right, let's look at one last example where we can use the quadratic equation to interpret some results. Imagine you have a group of friends trying to launch a water balloon into the air as high as possible. And the first balloon's path can be modeled by the quadratic equation shown here. It's y equals negative 16t squared plus 80t plus 5. Y is going to be the height of the balloon, and that's going to be after t seconds. The second balloon, the height of the second trial, is shown in the graph. So we can see here, once again, we're comparing t seconds to a height y. And this kind of makes sense. We have an initial height where it's launched and it increases in height, and then it starts to come back down before it lands on the ground. So in order to do this, I want to answer the question, which balloon went higher? Well, to figure that out, the maximum height is going to be at the vertex. And I can see here that the vertex is, based on this being a scale of 25, it's going to be somewhere just over 125. I can't tell exactly, but it's going to be something like that. So hopefully it's pretty clear from doing the work with the equation what the height of the vertex is there. In order to figure out the vertex, I once again go back to that formula for the axis of symmetry, which is x equals negative b over 2a. And for this, I'm going to use negative, now b is 80, over a is negative 16, so that's going to be over 2 times negative 16. That leaves me with negative 80 over negative 32. And if I reduce that, this will reduce to a positive 2.5 or 2.5. Now it makes sense here to use a decimal since we're talking about 2.5 seconds. Normally my equation involves x, but in this, because my variable has been replaced with a t, I could also use t instead of x if I wanted. So that is the x value at my vertex. Now I want to find the y value by using this equation right here. So I'm going to just plug in to y equals negative 16t squared, which is going to be negative 16 times 2.5 squared, plus 80t plus 5. I got to replace that t with 2.5. Forgot about that. I have to put it in both places there. I'll try to squeeze that in. And now I use the order of operations. So I first do 2.5 squared, which is going to be 6.25. Multiplying that by negative 16, I get, oh, that works out rather nicely, negative 100. Then when I do 80 times 2.5, I get 200 plus 5. This is going to give me a total maximum height of negative 100 plus 200 is 100, plus 5 is 105. So I'm going to hit a maximum height of 105 feet on my first trial. So let's just go back and remember, well, what was my maximum height from the second trial? Turns out that it's over 125. The 105 feet would be somewhere right around here. It's probably even higher than I want it to be, but that's okay. So you can see that the second balloon actually goes above that. That means I've improved on my second trial, and that's a good thing. So that's what you need to do. You need to use x equals negative b over 2a to find the x-coordinate of the vertex, plug that in to my equation to find the y value of the vertex, and that tells me the maximum value. Because my a was negative, I know this opens down and therefore has a maximum, as opposed to a quadratic where the a is positive and therefore would open up and have a minimum this has a negative a, therefore has a maximum at its peak. All right, I hope this was clear.